What specific problem does the GSM-Symbolic benchmark aim to solve in the evaluation of mathematical reasoning capabilities of LLMs, and why is it significant?
The GSM-Symbolic benchmark aims to address the limitations of the GSM-8K dataset by generating diverse variants of math questions using symbolic templates, which allows for a more nuanced evaluation of LLMs' mathematical reasoning capabilities. This is significant because it moves beyond single-point accuracy metrics, enabling a comprehensive understanding of LLM performance across various setups and complexities. The benchmark facilitates the exploration of LLM's robustness and reasoning abilities by adjusting question difficulty and generating multiple instances, which helps to uncover the inherent fragility and variability in their reasoning processes. Additionally, it highlights potential data contamination issues present in GSM-8K, as performance on GSM-Symbolic often drops significantly, indicating that LLMs may not be genuinely understanding mathematical concepts but rather relying on probabilistic pattern matching. Overall, GSM-Symbolic provides a more reliable evaluation framework that emphasizes the need for further research into the reasoning capabilities of LLMs.
How does the proposed method GSM-Symbolic work? Please illustrate step by step, including how templates are created and how questions are generated from them.
The proposed method GSM-Symbolic works by creating parsable templates from the original GSM-8K dataset to generate diverse question variants. First, the process begins with identifying variables, their domains, and necessary conditions to ensure the correctness of both the questions and answers. For example, since the questions are at a grade school level, a common condition is divisibility to ensure that answers are whole numbers. After establishing these templates, automated checks are performed to verify that none of the original variable values appear in the templates, and that the final answers match the original question's answers. Finally, for each template, 10 random samples are generated, and at least 2 models must answer each question correctly. Otherwise, the question undergoes manual review, ensuring a robust generation of questions that can effectively evaluate the reasoning capabilities of LLMs.
Can you provide a simple example that demonstrates the inner workings of the GSM-Symbolic benchmark, explaining how a question is transformed into a template and then modified?
The GSM-Symbolic benchmark transforms questions from the GSM-8K dataset into templates by identifying variables, their domains, and necessary conditions for correctness. For instance, a grade school math question might involve a variable representing a number that must be divisible to ensure the answer is a whole number. Once a template is created, automated checks are performed to ensure that none of the original variable values appear in the template, and that the final answer matches the original question's answer. After generating the templates, multiple instances are created by modifying the variable values while adhering to the established conditions, allowing for a diverse set of questions that maintain the same underlying structure. This process enables a more nuanced evaluation of LLM's performance across various setups, moving beyond single-point accuracy metrics.
What are the practical advantages of using GSM-Symbolic over the original GSM-8K dataset, particularly regarding the robustness and reliability of evaluation results?
The practical advantages of using GSM-Symbolic over the original GSM-8K dataset include its ability to generate diverse question variants and adjust complexity levels, which allows for a more nuanced evaluation of LLM's performance. Unlike GSM-8K, which provides a single metric on a fixed set of questions, GSM-Symbolic enables the assessment of LLMs across various setups, revealing performance as a distribution rather than a single point. This approach highlights the inherent fragility of LLM's reasoning capabilities, as performance varies significantly with minor changes in input, particularly with numerical values. Additionally, GSM-Symbolic mitigates the risk of data contamination that can skew results in GSM-8K, as it employs symbolic templates to create new instances. Overall, GSM-Symbolic offers a more reliable framework for understanding the strengths and weaknesses of LLMs in mathematical reasoning tasks.
How does the paper validate the effectiveness of GSM-Symbolic in assessing the mathematical reasoning abilities of LLMs? What experimental designs or metrics are used to test the models?
The paper validates the effectiveness of GSM-Symbolic in assessing the mathematical reasoning abilities of LLMs by introducing a framework that generates diverse question variants using symbolic templates, allowing for a nuanced evaluation beyond single-point accuracy metrics. The experimental design includes generating 50 samples per template from 100 templates, resulting in 5,000 total examples, which enables the analysis of performance distributions across various problem instances and difficulty levels. The authors conduct nearly 500 evaluations on different setups, comparing model performance on GSM-Symbolic against the original GSM-8K dataset to identify performance drops and variances. Metrics used include the distribution of performance across different sets, the impact of changing input tokens, proper names versus numerical values, and the correlation between question complexity, number of clauses, and model performance. These comprehensive evaluations reveal significant insights into the fragility and limitations of LLM's reasoning capabilities, emphasizing the need for more reliable assessment methodologies.
What key results did the authors find when comparing model performances on GSM-Symbolic versus GSM-8K, and what implications do these results have for understanding the reasoning capabilities of LLMs?
The authors found that model performance on GSM-Symbolic exhibited notable variance compared to GSM-8K, with performance drops indicating potential data contamination in the original GSM-8K dataset. Specifically, they observed that the performance of models on GSM-8K often deviated significantly from the center of the GSM-Symbolic performance distribution, suggesting an optimistic bias due to inadvertent overlap between training and test data. Additionally, the study revealed that models were more robust to changes in proper names than to numerical values, with performance degrading more significantly when numerical values were altered. This fragility in reasoning capabilities implies that LLMs do not engage in formal reasoning, but rather rely on probabilistic pattern matching, leading to inconsistent performance across different instances of similar questions. Overall, these findings underscore the need for more reliable evaluation methodologies to better understand the limitations of LLMs in mathematical reasoning tasks.